Okay, so thank you, Duncan. So thanks to the Ingun also and to the organizers. So here I will be talking about Quixote. Basically, I will be presenting results from the 10 to 20 gigahertz observations with the MFI. And today I'm speaking on behalf of the Quixote collaboration. So this is a photo that is a little bit out of date. It was taken in 2015. Around that time, there are some people that are members of the collaboration that are actually listening today, like Federica, Carlos, José Alberto, Mike, and few others. So, so this is a collaboration that is led by the Instituto de Astrofísica de Canarias and also the Instituto de Física de Cantabria and the University of Cambridge and Manchester are also participating in this consortium. And the Quixote is made of these two telescopes. So the Quixote first telescope is the one in the foreground. So this is was hosting the detectors between 10 and 20 gigahertz with angular resolutions between 0.9 and 0.6 degrees. It was operative between 2012 until 2018. And the telescope in the foreground is the Quixote Telescope 2. It's a replica of the first one. And this is extending the frequency coverage to 30 and 40 gigahertz with finer angular resolutions. So Mike already spoke about the Teide Observatory, so it's not worth to go into more details. So he said that the PWB median value is 3.8 millimeters, as is shown in this plot. And just to mention that the Quixote frequencies, the atmospheric temperatures in the zenith are between 2 and 8 Kelvin, typically. So that's the contribution from the atmosphere. That is a small contribution relative to the global system temperature of the instrument. So as Mike already said, in the Teide Observatory, there have been several other CMB experiments observing before this. So starting with the Tenerife experiment back in 1984, that produced these very nice maps of the CMB anisotropies. Also the IEC Bartol and this 33 gigahertz interferometer that also measured the first peak of the first acoustic peak of the power spectrum. Later, the Cosmosomas experiment came online. It was observing until 2007 and produced some very nice results of the concerning the characterization of diffuse foregrounds, and in particular, this SCD of the anomalous microwave emission in the Perseus molecular complex was one of the first detailed characterization of spinning gas emission in a compact region in this paper by Bob Watson in 2005. And then the very small array interferometer at 33 gigahertz produced these very nice maps of the CMB anisotropies and this power spectra of the CMB anisotropies between multiples 100 and 1500 in this paper led by Clive Dickinson in 2004. So nowadays, there are, in addition to Quixote, there are other experiments that are observing from this site. So they are spread around a relatively small area in the observatory. So Mike already spoke about Groundbird. But in addition to these two, there is also LSP Strip that is led by an Italian consortium led by the University of Milano at 43 and 80 gigahertz. We'll start observations hopefully next year. And also the Tenerife Microwave Spectrometer is an spectrometer working at covering the 10 to 20 gigahertz band and will be hopefully start observations in 2023. So this is the most of the results I will be speaking about today are based on the observations of the MFI, which is the multi-frequency instrument of Quixote covering the 10 to 20 gigahertz band. So it has 32 output channels in total, centered in 4 individual bands at 11, 13, 17, and 19 gigahertz with sensitivities, instantaneous sensitivities per channel of the order of 500 microkelvin per root of a second. So these are photos of different components. So this is the horns on the cryostat, horns covering the different frequency bands. These are the rotating polar modulators that are used to modulate the incoming polarization. This is a photo of a LNA, and this is the orthomode transducer. So the angular resolutions of this experiment is between 0.9 and 0.6 degrees, depending on the frequency, and very low near side lobes and far side lobes. And the F-NIS in polarization is of the order of 300 millihertz and 50 hertz in intensity. So the science niche of Quixote is pretty clear. So Stuart already spoke about that. So it's basically extending the frequency coverage in polarization provided by value map, as you know, starts at 23 gigahertz, Planck at 30 gigahertz. So it's extending the frequency coverage to low frequencies. And this is a very clear niche for Quixote and also for CIVAS. There is a need for low frequency observations in what concerns the characterization of the synchrotron polarization. And this will have a significant added value for future missions like LIBER. So the initial goal with which Quixote was conceived was to try to reach a sensitivity level at the map level in Q and U of the order of 10 microkelvin per beam of 1 square degree. And in order to do that, so we have done with MFI this observation program between 2013 and 2018. So we observed different individual patches of the sky that are depicted in this plot, different galactic regions that were integrated to higher sensitivity by using observation in raster scan mode. And some of these fields are indicated in this box. And on top of that, most of the observing time during that period was invested in the so-called wide survey of the full northern sky. So we invested a total of 11,000 hours in this survey in order to produce full northern sky maps at 4 individual frequencies, and which is what I will be speaking about later. So in total, during this period, we accumulated in total during the MFI lifetime 26,000 hours of observing data. So this corresponds to approximately 3 effective years. So in turn, this means that we have been observing during half of the time between 2013 and 2018. So this is this slide illustrates the main scientific results of this observation with MFI. So these first 3 papers have already been published, and this series of 13 papers will be presented the main results of this wide survey with the MFI. So this is the main paper that is led by José Alberto Rubiño Martín, and a series of 12 papers commenting the scientific results coming from those data. So 6 of these papers, the first 6 in this list are quite advanced and they are almost ready for submission. And the maps coming from the maps coming from this survey will be made publicly available right after the acceptance of these papers. So this slide is a summary of the first 3 papers with that have already been published, presenting QUIJOTE-MFI data. On the left, this is a paper that was published in 2015 using commissioning data on the Perseus molecular complex. So in this paper, we presented a characterization of the spinels emission on this molecular cloud, providing these 4 points pinning down from Quixote, pinning down the AME spectrum at low frequencies. So this paper was published in 2017, and here we observe a chunk of the galactic plane covering the W47 and W43 molecular complexes and the W44 supernova remnant. And in this paper, we presented these upper limits on the polarization fraction of the spinning dust emission in W43 that are actually the most stringent upper limits on the level of polarization of AME obtained up to date. So this limit is at the level, as you see, of 0.22%. In this other paper in 2019, we presented a characterization of the anomalous microwave emission across the Taurus molecular complex, and I was led by Frédéric Podeman in 2018. Well, so these maps in this slide present the main maps resulting from this wide survey I was mentioning before. So these are maps at 11, 13, 17, and 19 gigahertz of Stokes I, Q, and U. So as I said earlier, these maps come from a total of 11,000 hours of observing time. So after data flagging and masking, we retain 6,000 hours of data, which are indeed introduced into the production of these maps. They cover essentially the full northern sky, 29,000 square degrees, and reach a sensitivity level in polarization of between 35 and 40 microkelvin per beam of 1 square degree, and in intensity of about 60 and 150 microkelvin per degree, depending on the frequency band. So this is a the same map of the Stokes eye at 11 GHz that I showed in the previous slide. So this hole here is the North Celestial Pole. This stripe here is removed, is masked out in order to avoid RFI emission from geostationary satellite that are spread across declination 0. And this big hole is, of course, the southern sky that is not accessible from Tenerife. So there are obvious galactic features that you, most of you, I'm sure, will be able to recognize that are clearly detected in this map at 11 GHz. So this is the Stokes Q from Quixote at 11 GHz. And this is a comparison with the Dalumap 23. So here we have scaled the color bar in order to match, to the same amplitude as in Quixote, but extrapolating with an spectral index of -3. So essentially, you see that in Quixote, the color scales go from -1 to 1 millikelvin, and here the color scales goes from -0.11 to +0.11. So that corresponds to spectral index of -3. So you see a very clear and very good spatial matching between the features in Quixote and Dalumap. So this is the same for Stokes U. So this is U at 11 GHz, and this is U from 23 GHz. So the main aspects related with the pipeline and calibration and systematics effect associated with the production of these maps, and in general the overall data processing pipeline of Quixote, will be presented in this paper that is currently in preparation. And this slide presents some of the basic aspects that will be discussing more in depth in that paper. So essentially, the amplitude calibration, the external and global calibration, is based on point sources in Tawway and Kasei, basically. And this provides an accuracy in the amplitude calibration at the level of 5%. So this accuracy level is actually driven by the calibration models, and it's not internal to Quixote. So the intrinsic noise of Quixote is much better than this. So this calibration uncertainty is due to the external models we use to calibrate. On the other hand, as I said here, there are different pieces of evidence that makes us be confident that the internal gain modeling that is achieved through an internal calibration diode in front of the focal plane is better than 1%. The calibration of the polarization angle is based on the Tawway, and this leads to an accuracy of the level of 0.5 degrees. And the characterization of the beam and window functions is based on the bright point sources, Tawway and Kasei, and also in the emission of geostationary satellites that allow us to reach levels of the order of 30 to 40 decibels. In order to reach deeper levels, we resort to an optical model that is based on the CST software. And we actually have, as you see in this plot, this shows a comparison of the beam radar profiles from different point sources and from the optical model that is depicted here by this gray curve. So there is a very good matching between the point sources on the sky. So here in Kasei, you see a departure from the main beam at high angular distances, but that's produced by the surrounding background around Kasei. The pointing model, this is based on the bright point sources like Tawway, and this is done through a fitting of a 7-parameter model. And here we reach accuracies better than 1 arc minute. The RFI is corrected through masking and also removing, and in particular, we perform a removal of a constant mode of declination that leads to removal of power at multiples below 15, and the atmospheric correction in intensity. So we don't do any atmospheric correction in polarization. Is based on a PCA analysis in order to look for correlated signals between different horns. And these are the templates that are subtracted at 17 and 19 gigahertz, showing the diffuse, so the large scale atmospheric contamination that is subtracted from the data in total intensity. So in this paper, in the main paper that is led by Jose Alberto, we will be presenting a bunch of validation and different health checks that are applied to the data, some of which are shown here. So the global amplitude calibration is checked by comparison between different source models. So this is shown here in this plot in the bottom. And this shows that our calibration scale is good to within 5%. As I said before, the scatter here is driven not by intrinsic noise of our data, but by external calibration, by the uncertainties in the calibration models. So we also perform a cross-correlation analysis. So this is a work that was done by Federica Guidi during her PhD thesis through correlation of the Quixote frequency maps with the Planck-SMICA map. And this led to a detection of the amplitude of CMB anisotropies that is fully consistent with the level of expected level from SMICA, and with which actually in turns we achieve a detection at the 35 sigma level of the primordial CMB anisotropies. So we also perform a health check of the calibration amplitude accuracy using the dipole, and this map here actually shows a map of Quixote at 11 GHz with the dipole unsubtracted. So we are able to detect the dipole at 10 sigma, and the actual amplitude is also consistent within the expectation. The internal gain modeling is assessed through different null tests, the results of which are shown in these plots. And here we find, through this jackknife test, we find accuracy in the internal accuracy at the level of in the gain calibration at the level of 1% in intensity and at the level of 5 to 6% in polarization. This value is actually signal to noise limited, so the signal to noise in polarization is lower. So this is why the scattering the scatter in this case is driven by the noise and not by the statistical noise of the data, not by the systematic errors actually. Polarization angle calibration is also assessed through a comparison between the polarization directions using bright diffuse emissions in the Quixote and the LFI and Dalumap maps, and in particular when we compare the polarization directions at 11 GHz in Quixote and in Planck at 30 GHz, we find agreement within the 1 degree level. So in the rest of the talk, I will be flashing through some of the main, well, not some of the main, some of the results that will be presented in this series of papers associated with this release. So these slides in the left, I'm showing the composition in the E and B modes at 11 GHz. So in the left is the E mode map at 11 GHz. The right is the B mode map. So in the main paper and also in this paper that will be led by Flavien Van Singel, we will present a characterization of the power spectrum of this data of the synchrotron emission. And from this analysis, one of the main results is that we find B to EE ratio at the level of 0.25. So this compares to the value of 0.5 that is found in Planck for thermal dust emission. We also detect a positive TE cross-correlation at large angular scales, and we find EB and TB consistent with 0. So further details will be presented in the main paper led by Jose Alberto, and also in more details in this paper by Flavien Van Singel. In that paper, we will also present a characterization of the spectral dependency of the spectrum of the synchrotron emission at the power spectrum level. And one of the main results is that we find spectral index for the synchrotron polarization of -3.20. So this is consistent with the previous values found using Planck or SPAS data. In a different paper that is led by Elena de la Hoz, we present also, we will be presenting a detailed characterization of the spectral properties of the polarized synchrotron emission, but in this case at the map level. So in this paper, Elena applied her parametric component separation method, B-secret, to a combination of Quixote data, 11 and 13 GHz, and Dalumap 23 and 33, and all Planck polarization channels. So the main results are shown in this plot. So in the top is the spectral index of the synchrotron emission, and this is in the middle is the uncertainty with which we are able to recover the synchronous spectral index in pixel scales. So on the left, this is a combination of W map and Planck, and the second, the third, and the fourth column represent the gain that we get after the inclusion of MFI. So this is the MFI data in combination with Planck, MFI in combination with WMAP and Planck data release 4, MPIPE, and this is MFI, WMAP, and Planck data release 3. So basically, you see that after the inclusion of, in the uncertainty maps, you see that after the inclusion of Quixote data, the uncertainty with which we are able to recover the spectral index of the synchronous emission is notably reduced, as you see here. One of the important results from this paper is that we find compelling hints of spatial variability of the spectral index of the synchronous emission. So this plot here on the left shows the, in orange, we show the histogram of spectral indices at the pixel level that we find in Quixote. And essentially, we see an spectral index with a mean value of minus 3.08 with a scatter of 0.13. So this scatter, we believe, is real on the sky, so it's not driven by uncertainties nor the prior that is used in the component separation method. So we are confident that these are real sky variations of the spectral index of the synchronous emission, and the level of variability that is found is actually a factor 2.6 larger than what was found before in this paper by Marc-Antoine Miville-Deschênes in 2008, that is shown in this histogram in blue. So we detected a factor 3 larger variability. Another important result of this paper is the detection of curvature of the synchronous spectrum, mainly along the galactic plane. So we find when we assume a fixed value for this curvature parameter in the full sky, we get this value that is dominated by the emission along the galactic plane. So this is a significant detection of curvature of the synchronous spectrum along the galactic plane. However, we don't have sufficient signal to noise as to claim evidences for synchrotron curvature at high galactic latitudes. In what concerns the characterization of the anomalous molecular emission, this paper that is led by the Frédéric Podeban, we presented a characterization of AME in 54 individual combat clouds on the sky. So this is a follow-up study to what was done using Planck data in 2014. And one of the main results of this paper is an improved separation between the AME and free-free. This is illustrated in this plot. So in the vertical axis, you can see the level of AME that is recovered in this in compact clouds from the Planck analysis, and on the horizontal axis, you see our results. So basically, the introduction of Quixote data leads on average to higher AME and to lower free emission. So basically, by adding data in this 10 to 20 gigahertz range, we are able to better disentangle the free and AME degeneracy. We also perform a series of correlation analysis of different spin index parameters, and one of them is shown in this plot. So this is a correlation between the amplitude of AME normalized by the dust opacity in comparison to the intensity of the interstellar radiation field. So we find a clear correlation that was also previously claimed in other papers, and this is the well-known correlation between the AME amplitude and the peak of the thermal dust emission that is found with a very high correlation in this analysis. So this is another paper that was led by Roque Cepeda Arroita. It's already published in 2021, and this is a joint analysis between CIBAS and Quixote data in a particular region, in Lambda Orionis. So Lambda Orionis subtends around 10 by 10 degrees on the sky. So the combination of CIBAS and Quixote data allow us to perform a detailed spatial component separation of the different components. And in this plot, I show some of these maps of the different parameters. And one of the main results of this paper was the detection of the spatial variation of the spectral properties of the AME across this nebula. So for instance, in this plot, you see the peak AME frequency that is found to vary across this area. In this paper in preparation that is led by Mateo Fernandez Torreiro, we extended this analysis to the full galactic plane. And in this plot, you can see some of the results. So this is a map of the AME amplitude across the plane. And this is the AME uncertainty. And this is the signal to noise, the ratio between the two. So as I said, this is an extension of the previous analysis performing lambda Orionis, but to the full galactic plane. In what remains of my talk, I will be discussing about some future plans and instruments and experiments that will be observing from the Teide Observatory. So the TGI and FGI instruments are the high-frequency extensions of Quixote. So the TGI was conceived to have 31 pixels at 30 GHz with a full array sensitivity of 50 microkelvin per square root of a second. FGI is a similar instrument at 40 GHz with a similar level of sensitivity. And at the moment, we are performing observation with a joint configuration of 30 and 40 GHz pixels in the same focal plane. And we are commissioning this instrument at the moment. So these are preliminary commissioning characterization analysis from this data at 30 and 40 GHz. So this is a old map that was taken in back in 2016 using 30 GHz pixels. So this is emission of the moon showing the different positions of 30 GHz pixels in the focal plane. But in the bottom, these are recent observations, calibration observations of the Tau-A nebula at 30 and 40 GHz. On the right, on the left, sorry, these are power spectra of the noise properties of different 30 and 40 GHz pixels. So this is a preliminary data analysis, but from this data analysis, we are finding white noise levels of the order of 400 to 900 microkelvin per square root of a second per channel, with knee frequencies of the order of 20 to 50 hertz in intensity and below 100 millihertz in polarization. So you see the power spectra in polarization are pretty flat in some cases. So the knee frequencies are basically zero. So we don't see any rise of the 1/f in polarization. And in what comes to beam characterization, we are finding the full width half maximums that are according to the expected values of the order of 22 arc minutes at 30 GHz and 17 arc minutes at 40 GHz. The MFI2 instrument was conceived to be an upgraded version of the MFI with the goal to try to have, basically it's covering the same frequency range, 10 to 20 GHz, but improving the sensitivity by a factor of 3, and also with an improved RFI removal, thanks to the implementation of a full digital backend module implemented with the FPGAs. So this way we will be able to better remove RFI in individual subbands. So the overall goal is to, so this instrument is being fabricated at the moment. So we expect to start commissioning observations at the end of this year. And the global goal is to observe during 3 years, with the ultimate goal to improve the current sensitivity of the QUIJOTE-MFI maps by a factor of 4. So the final goal is to reach sensitivities at the map level of around 10 to 15 microkelvin per beam of 1 square degree. And if we extrapolate to 100 gigahertz with a spectral index of -3, this will lead to sensitivity which is around 1 microkelvin per arc minute. So this is more than 100 times better than what the Planck LFI at 1 gigahertz provides at the moment. So Stuart in his talk mentioned that CBAS is extrapolated to 100 gigahertz is 0.0 0.0125 microkelvin per degree. So this is more or less 1 microkelvin per arc minute. So this will be equivalent to the signal to noise that CBAS achieved at 5 GHz. Finally, the TMS is the Tenerife Microwave Spectrometer. So this is a different instrument. It's a low resolution spectrometer covering the 10 to 20 GHz band with a spectral resolution of 250 megahertz in 40 individual subbands with an angular resolution of 3 degrees. So this is conceived for CMB spectral deviations. We'll start observations in 2023, but it will be a nice complement to Quijote because in principle it will be able to provide absolute calibration scale for Quijote. So these are the summary and conclusions of my talk. So I have presented the maps coming from the MFI observations on Quijote Telescope 1, coming from observation between 2012 and 2018. So the maps that I showed cover the full northern sky, reach sensitivities of 40 microkelvin per beam of 1 degree. So I have commented some of the results that will be presented in these 13 papers. 6 of them will hopefully be submitted within 1 or 2 months time scale. And the maps will be released after the acceptance of these 6 papers. And some of the main results of those papers concern the characterization of the synchrotron emission. So we found spatial variability of the spectral index, also compelling hints for curvature of the spectrum in the galactic plane. I didn't mention earlier, but we also find a correlation of dust and synchrotron at the level of 20%. And in what concerns AME analysis, I think I have convinced you that Quijote brings a quite significant added value to this analysis, allowing to improve the separation between AME and free-free. And we also provided quite tight constraints on the level of polarization fraction of AME at the level of 0.2%. So the high frequency version of Quijote is implemented in the TGI and FGI instruments that are being commissioned at this moment, and the operations will extend until 2025. So we are planning for a 3-year survey. And at the moment, we are fabricating the MFI2, which is an upgraded version of the current MFI, aiming to improve the sensitivity of the current maps by a level of 3 or 4 in order to reach sensitivity levels of around 10 to 15 microkelvin per degree. Other experiments at the OT, so I mentioned LSP strip is a nice complement to Quijote, extending the frequency coverage to 40 and 90 GHz. Mike Peel already spoke about Gramber, 150 and 220 GHz. And I briefly mentioned the TMS, which is a spectrometer covering the 10 to 20 GHz band, which will be able to provide an absolute calibration for Quijote. So I end here. Thank you very much.